All right, good morning. Welcome to Wednesday of this week. One announcement, the hacker section is this evening at 7 p.m. in Maxwell Dworkin's Cafe, and why don't we begin with this little raffle. So if we were a humanities class, we probably would have just tossed the interested parties' names in a hat, but that's kind of lame, so we're going to instead write a little program. Why don't we call this thing raffle.c. I'll look to you guys for a little bit of input as to how to do this best. So let me go ahead and open up raffle.c. I'm going to go ahead and presumably we're going to want to print out the answer, so I'll include that thing there. We know we need a main routine. I'm going to go ahead and whip this up real fast. OK, and now we've got our little template here. All right, so in advance of class, what I went ahead and did and took our 30-some-odd contestants who emailed CS50 plus raffle over the past 2 days, and I put all of their names in an array. And just to keep the names somewhat private so you don't know exactly who entered, what I went ahead and did was put all of these names in a file called students.h. This isn't totally the right way to use a .h file, but it does allow us to just tuck those away for privacy's sake. So 30-some-odd names are in that file in an array called students. So I'll get us started, and I'll say that the size of this array, so that we don't have to count it up manually, we can do that little trick. All right, so we said last time that we can determine the size of an array in some contexts by doing what? If that array is called students. Is it as simple as this? No, it is not. So what does size of given an array actually return, if you recall? It's not the first something, but rather the total number of bytes. So the size in bytes. But these are students' names inside of this array. So what data type is each of those students' names stored as? A char star, which is a pointer, of course. And how much space does a pointer take up? Any pointer. 4 bytes is the answer, right? Or 32 bits, right? Any pointer, no matter what datum it points to, is 32 bits. So the implication is that that thing is essentially 4 times as big as it should be, because we've multiplied the total number of elements by 4 for the total number of bytes. Well, the dynamic way to figure this out, and this is a little trick that's not uncommon to see, is to use this little trick, where you take the total number of bytes divided by the size of just the 0th element, and that obviously gives us the answer without having to make any assumptions hard-coded into the code as to the size of these data types. All right, so there we go. Now I know how many students there are. Presumably we want to pseudo-randomly choose one of these n students. So what's the first step before when I want to use pseudo-random numbers? What do I need to do to make this as fair as possible, or at least as unpredictable as possible? Seed it. So we want to seed it with the function called srand. Srand takes an argument, the seed value. It's probably kind of silly to hard code that too. So what's the typical convention? Yeah, so we call the time function, and recall the usage for time. If you don't want to pass in a pointer, you have to pass in null to keep the compiler from complaining. And if I want to use this thing, recall, I actually need to include time.h up here. All right, and actually for srand and rand, I also need to include, I believe, standard lib. OK, so I've added that now as well. So now our PRNG has been seeded. Let's go ahead and say, just to make this kind of cute, all right, so rolling a, how about D, sided die, dot, dot, dot. And we'll plug in there the value n. How about? All right, so we're one step closer. And I'm using %d because the size is obviously an int. What do I want to do next? The goal, again, is to choose one of these students pseudo-randomly from the array of size n. OK, so divide what by? Yeah, so we're going to want to generate a random number and then take that number modulo the total number of students so that we don't get it back at an int from the range 0 to int max, which is huge, like 2 billion, but rather we have a value between 0 and n-1 inclusive. All right, so actually let's just make this a little more interesting, build up a little suspense. So I'm going to have a little loop here. Let's go ahead and run this thing maybe 100 times. I++, and just, again, to make things interesting here, I'll go ahead and say on each iteration, let's go ahead and we'll use this little trick so that we can make a little bit of an animation here, %d. Yeah, that's good enough. So we'll call rand, and then take your suggestion of doing rand modulo n. All right, so this is going to have the effect of generating, like we're rolling a die, it looks like 100 different random numbers, printing each to the screen. What's that \r going to do for me, though, precisely? Yeah, it's going to keep moving the cursor back to the beginning of the line so that we don't have this stupid-looking program that prints 100 different lines of numbers, but gives us sort of the illusion of a bit of animation. All right, before proceeding, before trying to print out anyone's name at all, let's go ahead and run this, compile and run this thing. So it seems to compile OK. And now I run it, but not ideally the effect we want. All right, so let's try to slow this thing down. All right, we printed, that loop executed 100 times. What can we use to slow things down and actually give it a pause? Yeah, sleep or micro sleep. Use sleep. All right, so sleep, let's give it 1 second since it expects a number of seconds. And then there's a header file I need to include to use sleep. So I rarely remember. So let's check the third section of the manual for sleep. And it looks like we just need this guy up here. So let's go ahead and copy that. We'll paste it into the program. All right, so put this up there. Save that. Recompile. Whoops, recompile. Raffle. Run raffle again. It seems to be pausing. If we wait long enough, we'll see that it paused 100 seconds worth of time. But why are we not seeing anything? What could be the problem? Code seems to be in pretty good shape. Nano raffle.c. So what's going on? I am printing, and then I'm sleeping, and then I'm printing, and then I'm sleeping. So what's the problem? Yeah? A little more basic than printf. What do you mean?
A little bit more down to send it out. Because when you sleep, then it also stops the printf.
OK, so when you sleep, it might very well be stopping the printf because it's sleeping the thread that my program is executing within. But I seem to be printing first, though. Right? And then I'm sleeping, then I'm printing. So what do you mean by simpler? What would you propose? I'm not sure what's complicated here. Like, just that?
Oh, no, the printf function itself.
So use something other than printf. Yeah. How am I going to get output to the screen? I mean, there's putchar, and there's these others, but they all, I mean, they're sort of just different ways of still manipulating the same file stream called standard out. So the reason for this, actually, let's do one thing. Instead of doing this \r, let's go back to sort of day one, where we just took this approach. And yeah, it's a little ugly, but let's see what happens. So let's run it now. And now it seems to be working. So some of you noticed a while back that in a couple of our examples, we did this \r thing, but then I had this command here, which we sort of waved our hands at and just said that needs to be there. We'll take a guess what a function called fflush is doing to standard output. Well, it's quite literally like flushing the stream. It's sort of forcing whatever's in it to come out of it. And the reason for this is that for performance's sake, typically, functions like printf and similar functions that have to do with file I/O don't necessarily exhibit their effects immediately, because it's sort of a waste of the computer's time to constantly just be constantly printing things out, just one character at a time, right? The function would rather, for performance's sake, maybe save up a bunch of characters and then dump everything out, just so that it only has to write to memory, for instance, once, or read from disk just once. But if aesthetically your goal is to actually see these things byte for byte for byte, well, sometimes you actually have to tell the computer, flush your stream now and stop using your little performance tricks or your efficiency tricks. So if I now recompile this using both \r and this flush of standard out, now we'll see that we have that sort of desired effect. But we're going to see a bug here in a moment. So it's fine that some of the numbers seem to be repeating occasionally, right? Because that's sort of to be expected just by chance. So the numbers are greater than 32. That's OK. So we actually have 30 some odd students in the array. So the biggest number is OK. So that was weird. I'll admit. So what's the problem, though? Yeah. Exactly. The pseudo-random number in that case must have been 8, and there were just remnants of the previous number there. Right, and actually, yeah, that's a good clue. So the fact that the cursor is sort of moving to show you the width of the number that was just printed sort of reveals, if we finally get, there we go. So in that case, it wasn't 62 that was generated, it was 6, but the previous value was something 2. So what's a quick aesthetic fix for this? So we could justify it, or really we want to specify the width of this thing. And maybe just for the sake of making sure that enough characters are being used, let's make sure that every number uses up 3 characters. And I'm doing the minus sign there just so that we keep things aligned on the left. But the implication now is that every number that prints is going to take up 3 spaces. And even if it's too short, it's just going to get padded, so to speak, with white space. So aesthetically, that'll have the effect of sort of erasing what was there before. So let's go ahead and rerun this after compiling. And now, even though we have this little aesthetic quirk of this cursor being slightly away, I'm fine with that if you are. Right? At least we're seeing the actual values. All right, but we actually haven't gotten to the very end here. The goal at the end here is to actually print someone's name. So why don't we go ahead now and say printf. We'll do that so that it appears on a new line. And the winner is, and then I'll do this. Maybe a little \n there. And now I have to index into the array that I promised was called students. I'm going to pick one final random number, modulo n, so that it's actually within the desired range. And what do you think? Pretty good pseudo-random number generator? OK, it's going to take an awfully long time to run this one. So why don't we actually change that back to 10? Well, let's go ahead and compile this thing. Any objections, though? Because this is it. The winner of the software will be determined by this. So make raffle. Let's go ahead and run raffle. Ooh, and here we go. Suspense. Oh, what do you know? What? Well, what is going on? All right, let's take a look. Oh, what do you know? OK. All right, so there's another file called realstudents.h. So let's remove that. Let's rebuild it and run raffle. And here we go again. Wasn't sure I'd get away with that. And our winner is Nina Han. Is Nina here? Nina, come on down. A big hand for Nina if we could. All right, congratulations. All right, any questions before we return our attention to things related to linked lists? No? All right, so let's throw down the most important question whenever we try to introduce new stuff. Who cares, right? Why introduce these things at all? What's the motivation for this data structure known as a linked list? Perhaps you don't care. Go on. Yeah. Adding and taking out things. Yeah, which is not as easy in an array. And remember, one of the biggest problems with an array for doing things like insertions and deletions is that even though you can maybe get the data in there really quickly, if you want to get it into the right place and keep things sorted, you're going to have to move things around potentially. You're going to have to shrink things. You're going to have to reallocate memory and free memory. And these things tend to be expensive. And it just seems silly to be doing all this work just to do these very simple operations. In fact, if you use an array to represent a whole bunch of integers, and you want to keep them in sorted order, which is reasonable for any problem where you might want to do lookups efficiently with like binary search, what is the big O running time of the insert function if you're given an array that must be maintained sorted? What's the big O running time of the notion of insert into such a data structure? Sorry? So it's not as bad as n squared necessarily. But I did hear over here, so n. So in the worst case, if you've got an array that you want to insert some piece of data into, well, let's suppose for the sake of argument that there actually is some blank space here, and maybe we just have the numbers 2, 4, 6, 8 here, and we want to nicely enough insert the number 10. Well, in this case, Well, if we don't know where the free space is, well, we might in fact have to iterate over the whole array looking for maybe some sentinel value, or maybe using a variable we remembered that the nth location of this array, or nth minus 1 location, happens to be free. But suppose this thing is maybe all filled with numbers, and it's the number 10. And I now want to go and insert the number 9. All right, well, just to find the location might, in the worst case, take n steps, because we almost have to reach the end. But then there's an even worse problem here. What do we clearly have to do if we want to fit the number 9 into our data structure? Well, we need to make a new one, like we discussed last time, and maybe it'll be just one bigger, though that's probably not the best foresight. Maybe we want to double the size just to give ourselves a bit of room for growth. But even then, if we're doubling the size of the array and creating a new one with malloc, that's not necessarily a bad thing. But what do we now need to do with these data? We need to copy them. And that, by nature, is going to be an O of n operation, because you have to copy every element over to the new array. So just to do something simple, inserting one number can, in the grand scheme of things, be fairly expensive. And same deal for delete. If you want to delete something from the middle of the list, but you don't want to have a gaping hole in your structure, in the worst case, you might have to shift all of your elements down, or maybe all of your elements up, or create a new smaller array and then copy the remaining elements there. So again, it's big O of n. But it's not necessarily, it doesn't need to be as bad as big O of n squared, because the rest of the numbers are sorted. And that's actually a good thing, because it's not as expensive to keep things further sorted. So now we have linked lists. So in sort of an English sentence, what's the general idea behind a linked list? I mean, that's clearly the picture, but what does that mean? How do these things work? Yeah. Okay. Perfect. So instead of having one big chunk of contiguous memory that you just assume is broken up into equal size chunks that you can then access just by walking through this chunk of memory, you instead instantiate, so to speak, each of these chunks of memory probably one at a time. But you somehow create linkages among them by way of what construct that we've introduced rather recently? A pointer, obviously. And that's just the address of the next thing in memory. So aesthetically, we'll typically draw these things as a nice long line. But the fact that the lines aren't butting up against each other in these pictures is meant to imply that these things could be anywhere in your computer's RAM. And it doesn't really matter to you. So this was the representation. We talked last time about the idea of traversal, and we came up with that little framework for testing things, letting the user insert, add, delete, and such. But we didn't actually implement insertion or deletion. So let's consider this. This is a redrawing of the same picture up here. And this is perhaps the state of our world when we've already got 5 integers stored in this linked list. What's the most important thing to bear in mind about the last element, as my drawing and that one suggests, albeit with different syntax? Yeah, so it's got to point to null. If it's just pointing off into no man's land somewhere else in RAM, you could very well be traipsing through your list to no end and ultimately touching memory that is not, in fact, your own. So you have to be careful there. So now just conceptually, if we want to insert an element like the number 20 into this list, just conceptually, what do we want to do? Well, the linked list, even though we as humans can see everything at once, from the computer's perspective, what is a linked list represented with? Just this thing, right? Just the so-called first pointer. And that's all we need, because everything else hangs off of that in a sense. So this is where we begin our story. The goal now is to insert the number 20 into this list. So what do I want to do? And we'll use my fingers as the sort of physical incarnation of these pointers. What do I want to do? So I want to insert the number 20. Where might it possibly be in the list? There's sort of 3 different cases, even as this slide suggests. Well, one case is it's going to belong right there, the new number, and that's probably pretty easy to deal with. Maybe it's going to end up over there, but then everywhere in between, so far as coding is concerned, is probably an equivalent case. So just intuitively, hopefully there's just 3 different cases to consider. I chose 20, so let's assume that this thing is going to end up in the middle of this list, as it should, to keep it sorted. So the first thing I'm going to want to do, much like my traversal, is declare some kind of pointer. Maybe we'll call it a pred pointer for predecessor pointer. This thing is just going to be a chunk of memory, and we're going to initialize it to the same thing that first points to, namely the start of the list. And now I'm just going to do like a while loop or a for loop. But what am I going to check on each iteration of this loop, where just like traversal, on each iteration, I'm updating the pointer to point to next, to point to next. And what am I constantly checking for? Null, right? I want to stop this iteration as soon as I see null, lest I walk myself off the end of the list. But I don't want to just check for null on each iteration. What do I clearly want to check for if the goal is to insert a number like 20 into a sorted list? Right? I mean, what do I need to obviously be checking to maintain that invariant of sortedness? And the value, right? So the numbers in these actual elements. So right now I'm pointing to this thing. I'm going to check presumably the value 9. So is 20, let's say, less than 9? Well, clearly not. So I want to update my pointer to the next field. Is 20 less than 17? Well, no, I have to continue onward. Is 20 less than 22? OK, yes, now it in fact is. So at this point in the story, and I'll draw the arrow in a certain way so that it's consistent with the code we're about to see, let's suppose because this thing is called a predecessor pointer, that even though I was sort of walking myself through this, ideally, if I'm going to insert a node into this list, I can't just keep blindly forging ahead with just one pointer. Right? If I reach this point in my story and I want to insert 20, what's the problem? Right, so there's no arrows going in the other direction, which means I'm sort of screwed at this point, because I don't know how to insert 20 into this list. I can put 20 here, for instance. Let's instantiate 20 with a call to malloc. We're going to put the number 20 into this node. And I can very easily update his next pointer to point to 22. But if my finger, my only temporary variable, is already pointing at this guy, I can't fix the list. Right? The list is still effectively going to look like this one-way train going in this direction, even though this guy happens to be pointing as well. So the reason that I sort of in advance realized I need this predecessor pointer is that I need to stay, I can't get one step ahead of myself. So rather, I want to really keep my finger here and then look ahead at the next node and check its value. And if the node I'm trying to insert, 20, is less than the next node's value, then I can actually update this guy's pointer to point here. And what's the final step? All right, just, I mean, conceptually, this isn't even like computer science so much as it is what you would expect. Let's update that pointer. And now, even though things aesthetically don't look as nice, we have a newly inserted node. Agree? Disagree? All right, let's consider the other cases. What if the thing is at the so-called tail or end of the list, and I want to insert the number 55? Well, the story might be the same. I can sort of iterate through the whole list, and now I get to this last node, 34, it seems. All right, at this point, 55 is not less than 34, so 55 obviously belongs at the end of the list. Turns out this case is a little easier. What does it take to insert 55 now, which I'll have to also instantiate with malloc? How do I put him at the end of the list? Yeah, so I need a pointer to null here, because he's going to become the new n. So I can't just leave that as some undefined value. And what's left? Yeah, right? Just update this guy. So he was previously null. I just need to update that node's next value. And now I've got that thing inserted. So not bad, yeah. Ah, great question. I'll put it back to you all. Do you have to traverse the whole list to find, say, that location? Yeah.
Yeah, that's kind of one of the downsides. There's no random access like a grid.
Yeah, exactly. So short answer, yes, you do have to traverse the whole list, at least given this design. And again, here's that theme of trade-offs, right? We now have sort of improved the state of our world because we now have this dynamism, but it's come at a price. No longer do we have random access, big O of 1 lookup times. Now the operation called find might take as many as n steps. And find is sort of an inherent subroutine in this notion of insert. So good question. All right, there's one other case. What about the head? This guy's not too hard either. Right? So if I want to insert now the number 5, I also need to declare a new node. So I'll just declare this in malloc. With malloc, it's going to end up somewhere in memory. 5 is clearly less than 9. So what do I need to update? Well, this guy's got to point to the former first node. And then what's the last thing I need to change? Yeah. So first gets changed. Now, I sort of did things with a bit of foresight, always updating the correct pointer. But notice that the order in which I change those arrows is rather terribly important. right? Consider, if we rewind our story for just one example's sake, to the point we were at a moment ago, where we had just allocated this node 5, and who knows what its pointer is pointing to at the moment. And at this point in the story, recall that first was still pointing here. Suppose that, just because I know what my goals are, I need to update the next pointer, and I need to update my first pointer. Suppose I do that in, say, different order. So let's go ahead and update first to point to this new node. And now I want to update this next pointer to point to sort of a problem, right? I no longer know where the head of the list was. I just lost or orphaned, so to speak, my whole linked list. So order of these things is, of course, important so that we can actually reach that state. All right, let's take a look, before we look at code, then, at the idea of deletion. But these two, in sort of picture form, should be fairly intuitive. So the goal of deletion, in this case, is to get rid of 22. So we're going to have to traverse the list somehow, presumably using a pointer called PTR, maybe pred pointer again, walking through the list, looking for the element. And if we find it, conceptually, what do we need to do? We need to, 1, free that node at some point. But what else must we do if the goal is to get rid of 22? And it's fine if you read it right off the picture's implication. We need to what? So we need to merge the two. We sort of need to stitch the left neighbor and the right neighbor together. So we update 20's next pointer to point to 29. And then anything else? No, that's it. The list only gets linked in this rightward direction. And so we call free before or after we do that. So it's got to be after. Because if you call free before you update that pointer, you're going to be using a pointer that's no longer yours to touch. Right? Because you're stealing the address of this node from where in order to put it there? Yeah, from this guy's next node. So again, order of operations important. How about the tail? Tail's actually pretty easy. What's the thing you have to do? Suppose we want to get rid of 34. We've traipsed through the list. We realize, oh, this thing's at the end of the list. What do you need to do? All right, so change the pred pointer's node to null, so his next pointer to null, and then just free the thing. But we're going to need a temporary variable there, too, so that we can change the next pointer of 29 to null, and then free this guy. Finally, head, sort of the same idea. So if we want to delete from the head, like number 5, we just have to update first to point to the previous first node's next node, and then we can free that node as well. So let's take a look at this in code. And today you do have a printout, since it's a bit more involved than the functions last time. So let's go ahead into list1.c. And I'll myself open up list1.h just to remind you that this was the structure from yesterday. We have an int n and a pointer called next. So here's the code from yesterday. Remember that this program, just to remind you of what it looked like, was to do this. Gives us a menu. Let's insert the number 1. List is now 1. Let's do another insert the number 3. OK, and we'll do one more insert the number 5. And then just for fun, I'll go ahead and delete the number 3. And so it looks like this implementation is working thus far. But again, that was the Julia Child approach, where we didn't actually implement those things ourselves on Monday. So let's consider, how about delete? And I'll walk us through some of this code, but realize that this example code should hopefully prove quite a useful reference come problem set 5, when you're implementing your fastest spell checker possible, because you'll use similar data structures there. So it's OK if you don't walk away with a perfect understanding of it today, but just realize that it's here. All right, so the first thing this function does is it asks us, what's the number to delete? We get that number, took it away in n. And now here I go ahead and declare my temporary variable called PTR, pointer. And I'm going to initialize that to the start of the list. So the goal is to delete. So I'm going to initialize my finger, essentially, to point to the start of the list, which is going to be the first node. But I've got to do a check. So I'm also going to declare this pred pointer so that I can have not only one finger pointing to this node, but then always, or almost always, another finger pointing to the previous guy. The goal being to stitch two nodes together if need be, upon deleting one in the middle. All right, so while PTR is not equal to null, what's this doing here? So if PTR n equals n. All right, well, this is the case of deleting from the head of the list. So if the very first thing you encounter is the idea of n, the number the user typed, equaling the current node's n value, so there again we're seeing the arrow notation, what do we need to check? Well, and this took some thought to get the code right, because unfortunately the story in slides is much easier to tell, I think, conceptually than actually coding this up. But there's two possible cases to consider. If ptr's n equals the number that the user typed in, it could be, because we're in this loop, that we're at the start of the list, or maybe we're actually in the middle of the list. It's sort of unclear at this point. So let's check. If the current pointer is still pointing at the very first element, that is, this is our first iteration, well, here's this bit of code. What are these two lines effectively doing? So it's updating first to point to that current node called pointers next pointer. So that literally is implementing this arrow here, this updated arrow. And then finally, we're freeing the node. So what we've just implemented in these few lines of code is this concept here. Okay? If instead, though, that this node happens to be at the middle or the tail of the list, what do we need to do instead? Well, it turns out that those cases aren't all that different. So if the thing happens to be at the tail, remember that our goal was to take the current node and do what with it? What do we need to do to initialize something, to actually remove an element if it's at the tail? So at this point in the story, pred pointer, as this slide suggests, is pointing at 29, and PTR happens to be pointing at 34. Because again, the scenario in question is the thing is at the tail of the linked list. All right, so what does it take to actually remove 34 from this node? Well, we said earlier that you can just change 29's next pointer to what? Null. But we can actually be a bit more general than that, right? And handle sort of two cases at once here. Because what is the last element's next pointer already? Null, which just in general, even if he's in the middle of the list, that points to the next element. If this element just happens to be the end of the list, fine, it's just null. Which is to say that in code, we can update the previous guy's next pointer to point to the current guy's next pointer. So here's the previous guy, 29. Change his next pointer to equal the current guy's next pointer. So that has the effect of putting null here in this case. But consider this. Update the previous guy's next pointer to equal the current guy's next pointer, which is the same thing as saying this address. Yes? No? So in code, even though I could have broken this down into two cases, it doesn't matter. Because in code, they're actually equivalent. You don't have to special case the idea of hard coding null. And that's it, at least up here. So that's all it takes in code to delete this node. But again, the order of operations is important. Update the list so that you're stitching the guy before and the guy after, if any, together. And then go ahead and free the guy who's in the middle. But what's the other case? If the current node's n value is not equal to n, what do we need to do? Keep moving, right? That just means that I'm looking, say, for the number 22, but I'm pointing here. It's not equal. I need to now update my pointer, and keep looking for this guy. Well, that notation we can steal from Monday. It was just this. Let's update PTR to equal PTR next. But if we want to have my trailing left hand behind me, I first need to say pred pointer gets pointer, so that I remember what that value is. And that's it for delete. And then I call traverse just so that we can see what the result is. OK, so any questions? And do speak up, because this is perhaps the most sophisticated code we've yet looked at, just because it's getting the problems conceptually are getting more interesting. And as the result, the code needs to be even more precise. Yay? Nay? Yeah. In this case here? So you know at this point in the story that PTR is pointing to, say, one of these data structures. And you know that each of these data structures, by definition, in my header file, has both an n value and a next value. So we don't know what this value is, but we do know conceptually that in order to move on to the next element, I need to follow that pointer. And to do that, you can simply say PTR gets the value of its next pointer, which means conceptually move your pointer over here. That makes sense. Good question. Other questions? All right, at the risk of scaring, let's look finally at insert. All right, so insert's a little different in that we first need to instantiate this node. So I'm going to go ahead and assume that it's going to be safe to instantiate this node. How do I do this? Well, we've seen this code before. We've never done it with a node, but the code is the same. I want to allocate with malloc enough space to fit a node that's of this size. And the nice thing about size of, again, here is this dynamism. You've defined, or we've defined, what a node looks like here. And knowing what I know about Linux and this particular x86 architecture and C, I could add up these values. In fact, how big is a node object? Just based on what you know about these data types. So it's not just 32, it's 8 bytes, right? Because we have 4 bytes for the int. And then a pointer, we've said, is always 4 bytes. So we know that this thing is already 8 bytes. But why bother making any assumptions or doing the math yourself? Size of can figure this stuff out dynamically, especially since on different types of computers, an int can be of different sizes. So you don't want to make those assumptions. All right, why am I doing this? Yeah. So if there wasn't enough memory left, maybe this is the 2 billionth node that I've tried to allocate, and the operating system has just had it at this point. It just doesn't have enough RAM. I need to check for that and just return so that I'm not actually assuming that this memory is legit. Otherwise, I'm going to go and say, print the number to insert, or number to insert. I'm going to put that number in the data structure. So notice two times ago when we looked at data structures, we used to use this dot notation to access a struct's data members. Why have we since changed today and Monday to arrows? Yeah? Right. So, well, it's the same as dereferencing the pointer and then using a dot. But in short, the rule of thumb is if you're actually trying to get at a pointer's data member, use the arrow notation. But if you instead actually had the node defined like this, node foo, then you could actually say things like that. But that's different. Okay? And actually, just to get a little crazy here, if this isn't too far, if I say bar is a pointer to a node, and I say this, how do I then change the value of n within this same data structure? Right? So now it's 13 instead. Agree? Disagree? Hopefully you agree. Okay. All right, back to the story. All right, so what do I do first? So it turns out there's a few cases to consider. And this is sort of the first in several lessons of thinking through code as carefully as possible, because you need to consider all the cases lest you end up with your increasingly familiar segmentation fault. So at the top of this file, we're checking for the empty list, right? Because if there are no elements in here, I better not start traversing this list. Because if the list is empty, what do we know is true about the variable called first? Again, the answers are almost always on the board today. What is true about the variable called first if the list has nothing in it? It's null, right? That's how we sort of represent underneath the hood that the list is empty. So if the list is empty, this is actually so easy to add this node to the list, no matter what its number is. If the list begins as completely empty, which means that our world right now looks like this, well, if I've just instantiated with that call to malloc a new node with some number, maybe 5, and actually, we don't know what that value is. If I just want to, actually, we did we? Yep, we set it already to null. So right now the story looks like this. If the list is already empty, it's so easy to add this element. You just do that conceptually, right? And then we're done. And so this first chunk of code here is doing quite simply that, where the blinking cursor is. New pointer is currently pointing, so that you can see, to this thing, and that's it. Well, what's the next case? All right, well, the next case is maybe this number belongs at the front of the list, at the head of the list. Well, how do we determine as much? Well, I'm checking if the new pointer's n value, 5 maybe, is less than the first node's n value. Right? If that's the case, the new guy clearly belongs before him. So what does it take conceptually to put this new node before the first node? Well, what do we need to do? So at this point in the story, we have, say, let's make this concrete. So at this point in this story, we maybe have a node with 6. That's the end of the list. Here we have the list. So that's the state of our world right now. All right, and clearly 5 belongs to the left of 6, so it belongs at the head of the list. So what do I need to do to insert this guy into this list in English? Good. So point this guy to 6, and then point first to this node. Done. Man, you'd have thought the candy would have actually made this a little easier today. But no, maybe the sugar high is coming down. All right. So, all right, I'm just going to start answering my own questions. Is this correct? Yeah, it's pretty good code at this point, right? Because that's simply embodying the idea of updating this guy first, new pointers next field where my cursor is blinking, and then doing first gets the address of the new node. Okay, finally, and thank God we're at else, right? Because this is the last branch. Else, try to insert the number in the middle or tail. And this is why I say things are getting, it's not many lines of code, but it's starting to feel like you have to think this stuff through carefully. And frankly, I had 2 TFs vet my code to make sure I didn't give you bad code today for that reason. All right, so here we have at the top of this line, so-called pred pointer. Because if this thing's going to be inserted now into the middle or maybe end of the list, now I need to be a little more sophisticated and keep more information around so I can actually fix this list and stitch it together if need be. So while true, I'm going to do the following. First, and I'm going to introduce this assumption now, I don't want the list to have duplicates because that just seems silly if all we're storing is ints. All right, so that's the decision I made. So if the previous guy is pointing to the previous guy's end value equals the new guy's end value, forget it. Just free the new node that we already allocated, break, and call it a day. Let's not even proceed. OK, now push back on me here. There's a potential inefficiency or stupidity in this design. For what reason? OK, too many lines of code. Not what I'm looking for, and I would actually say that it's hard to do this in many fewer, but that's fine. Keep pushing back. What's sort of just counterproductive about what we're doing in this block? Right, we clearly didn't need to allocate that guy in the first place, right? I sort of made this leap of faith at the first line of code. All right, let's go ahead and declare this new node. Conceptually, I like that, because now it's sort of ready and waiting to get inserted anywhere in the list. But the problem is there is at least one circumstance in which I don't need that node after all, and so I'm going to free it. So, right decision, wrong decision? Well, what's the alternative, right? We can sort of reason through this. If I didn't want to risk this inefficiency, where else could I have just instantiated the node? Yeah, so within the conditions that I am actually using it. So I could have factored this out, taken those 3 lines of code, and over here where I first put it in, why don't I put it there, that code? And then why don't I put this here, but now I'm going to need this here? And I'm intentionally doing this a little messy only because I could copy and paste this a few more times, but now what's a downside? Push back on this approach. Now we were getting redundancy of code, and I have the same blocks of code here and here and here. OK, so what's an obvious solution that we've been preaching sometimes? All right, so we could factor it out to an entire function, and maybe that would have been reasonable too. But I'll push back on my own code, and for the sake of simplicity, because frankly I was trying to isolate all the code to individual functions, if only for pedagogy's sake today. But arguably, this case here, where we have duplicates, I'm going to assume, maybe reasonably, that that's a pretty rare case. In which case, if this is the infrequent case that there happens to be a duplicate, maybe I don't care about wasting a few cycles, wasting a few micro or milliseconds to free up the memory and then return. So hopefully the takeaway here is that there's not one right answer here, but there are some potentially interesting questions. And when we talk about the design component of one's grade for these programs, I mean, these are the kinds of thoughts. And frankly, if you push back on us with comments saying, here's what I did and here's why I do it, it's often hard to argue with the developer if they've at least thought it through and can make a reasonable argument. So there is no one answer to that question as to why I did it this way. All right, what about here? If instead it's not a duplicate, but in fact it does belong in the list, check for insertion at tail. So what is this? Why does this work? Why does that one line of code have the effect of checking whether we're at the end of the list? Well, it sort of means that at this point in the story, this hand is here, and his next pointer happens to equal null, which means that's it for the list, right? So that's a way of checking implicitly for the end of the list. Now, push back on me here, too. How else could we detect if we're at the end of a linked list? So if the pointer is null, but that's this approach, right? Then we're checking this thing effectively. What's another approach? Think outside the box, if you will. I mean, actually, rather literally. So why not just keep around maybe this extra pointer, call it last, which just for convenience's sake, maybe efficiency's sake, always points to the end of your list, right? Maybe this gives you the advantage of the following. If I realize the user's trying to insert a really big number, heck, let me start iterating from the end of the list in hopes of not changing my big O running time per se, because all of that asymptotically is the same, but rather maybe I can, in real terms, save a few cycles, save a few iterations. Good? Bad? What do you think? Yeah, I mean, it's sort of there too, depends, but the idea that's introduced there is actually the idea of an alternative approach altogether, namely a doubly linked list. So I'm not going to dwell on the rest of insert only because I don't think it's terribly more enlightening. It's probably better looked at on one's own, especially from problem set 5. But take a look at this data structure. Now we appear to be representing the concept of a linked list with a slightly more sophisticated structure in that for this list, we don't just keep around one variable called first, but we appear to be keeping around an actual structure, here called L, that inside of it has 3 different variables. One is last, one is first, and one is my size. Now notice too, the data structure itself has twice as many pointers. One that points to the left always, and one that points to the right always. And there's this circularity. Actually no circularity in this list. So it still flows from left to right. But what do you think intuitively is the advantage of now having arrows in both directions? I mean, again, who cares? Why do this? Yeah, so obviously you can travel in both directions now, and that's perhaps advantageous because if you walk through the code that I wrote, arguably it's a little complicated maintaining these 2 pointers simultaneously as you're walking through the list. Wouldn't it be nicer if you can just iterate, as we've been doing with traverse, through the list, find where the node belongs, and then as soon as you know, just look to the left node by the left pointer to stitch it together with the next one. In other words, these changes to your data structure might make what easier? The actual code that uses the data structure, right? And developers' time and the developer's complexity is one of these trade-offs that is perhaps a valid metric. What about my size? I mean, that's a new idea altogether. What's the advantage of keeping around the size of the list in the actual list structure itself? Yeah? OK, so maybe if my size happens to be really big, maybe then you might indeed want to start looking at the end of the list if the user's number happens to be big. But even then, if you don't know anything a priori about the numbers being inserted, it might not be useful, but maybe it is.
It makes it really easy to implement just a loop, for loop.
So a for loop now becomes a little easier because you can literally revert back to the sort of week 1 approach to a loop where you iterate a fixed number of times based on that variable rather than constantly checking for what special value. Null, and so that's perhaps a nice thing too. What about just running time? I mean, it's a reasonable question to ask, how big is this list? Right? If you want to ask any database, how many students are in this database? How many records are in this database? That's not an uncommon question. But unfortunately, with a linked list, what's the running time of an operation like size for a linked list? It's n, always. You have to count every darn element just to get back a simple answer. Better, maybe in that spirit of memoization, but it's not quite the right word here, just to cache the size of the list. But what needs to change if you're maintaining in the struct itself the size? What functions need to be modified? So at the inserts, the deletes, and that's pretty much it. Those are the only ones that might change it. But now let's take one step back. So with linked lists, generally speaking, what's the running time then of find? So it's big O of n, right? Worst case, the thing's at the end of the list, or maybe it's at the beginning of the list, but you started looking from the end of the list. So it sort of depends on your linked list structure. What about the running time of insert? Worst case for a linked list. Big O of n again. What about delete? OK, big O of n. And again, we're making some assumptions. I'm assuming a sorted list, because actually the running time of insert, if you don't care about keeping the list sorted, becomes what? just order of 1, right? Just plop the thing at the front of the list, just always, arbitrarily. So it turns out that we can do better. It turns out there are data structures, one of which is called a hash table, that allows us to whittle down, in theory, the running time of things like find and insert and delete, all of them, to constant running time, an individual operation, which is a huge, at least on first glance, improvement. Unfortunately, there will come a cost, but we'll look at that on Friday.